In 3.1 we're to state what is meant by a capacitance of 370 microfarads. Well, this means the capacitor can store 370 microcoulombs of charge for every 1 volt of potential difference across it. In 3.2 we have a circuit and we're to calculate the resistance of R. Well, we know that time constant is equal to capacitance times resistance, and so resistance is the time constant over the capacitance, which in this case is 1 second over 370 times 10 to the minus 6 farads, and that gives a resistance of 2.7 times 10 to the 3 ohms, or 2.7 kilo ohms. In 3.3 we have axes of a graph, something like this, with potential difference against time, and where to place an X on the graph when the potential difference, when the switch has been closed for 2 seconds. Then we need to use X is equal to X naught 1 minus e to the minus t over CR, where X in this case is the potential difference at time t. X naught will be the final potential difference as the capacitor charges up. That will be 9.8 volts of the supply, 1 minus e to the minus 2 over 1, so we have a time constant CR of 1 second. This comes out at 8.5 volts, and that is around about here on the graph, and we join with a curve starting from 0 and curving something like that. For 3.4, we're to find the time taken for the charging current to fall to half its initial value. Well, for this we can use X equals X naught e to the minus t over CR, and X over X naught, in this case the current over the initial current, is equal to e to the minus t over CR, and we can inverse both sides to get X naught over X is equal to e to the t over CR. Inverting that side flips them over, inverting this side loses the minus sign. The initial current over the current when it's fallen to half its initial value is 2. So then we can take natural logs of both sides, and the natural log of 2 is then equal to the natural log of e to the t, I've lost the minus sign, over CR. The natural log of e to a power is just the power, so we have that the natural log of 2 is just equal to t over CR. So then t is CR times log 2, and this comes out at 1 times log 2, which is 0.69 seconds. In 3.5, we're to find the time taken for the charge to reach 3 millicoulombs. Well, again we can use X is equal to X naught 1 minus e to the minus t over CR, and X naught in this case is equal to the capacitance times the voltage, which is 370 microfarads times the 9.8 volts, which is 3.626 times 10 to the minus 3 coulombs. Then we want to know when it's 3 millicoulombs, and the maximum will be 3.626 millicoulombs. So then, using this equation again, we have 3 times 10 to the minus 3 is equal to 3.626 times 10 to the minus 3, 1 minus e to the minus t over CR. So we can cancel the times 10 to the minus 3's, and we have 3 over 3.626 is equal to 1 minus e minus t over CR, and 3 over 3.626 minus 1 comes out at 0.83. Therefore, e to the minus t over CR is equal to, I'm taking this across to the other side, bring this across to this side, 1 minus 0.83, which is 0.17. So then the natural log of e to the minus t over CR will equal the natural log of 0.17. But the natural log of e to the minus t over CR is just minus t over CR. CR, don't forget, is 1, so we end up with t being 1.77 seconds, or 1.8 seconds, two significant figures.